Okay, today we're going to start with some simple calculus, and then we're going to do some simple linear algebra. So the first thing is an aside that shows you the way that EIT is related to other PDEs. And so if instead of the EIT equation, we consider this equation. And so in EIT, gamma squared is sigma the conductivity and Q equals 0. But this equation covers a variety of situations depending on whether you allow Q to change sign. For example, it turns up in diffuse optical tomography, where the coefficients are related to both scattering and absorption. You could regard it as Helmholtz or Schrödinger's equation with a variable potential Q, or Helmholtz, you'd have to have Q negative, and that would be the wave speed. So, as an exercise, if you want to take gamma constant and Q variable, you can do what we did last week, which is work out the perturbation calculation. So I put that as a homework, and the only thing you have to worry about is that you actually have an inverse for the operator, a Green's operator, and if it actually is Helmholtz, in other words, a wave equation, Q negative, that would be kind of wave equation, then it could have some eigen functions, in which case the operator wouldn't be invertible, right? Because it would have several solutions, the eigenfunctions. But for Q positive, it's got a unique solution, and same thing holds. But here's the rub, that actually, if you think of this as a standard EIT type problem, where you know the Dirichlet to Neumann map, then you can't find both gamma and Q, and that's important in optical tomography, for example. And that's because there's a way of trading them off. In fact, there's a way of turning that equation into that equation. So they're actually very, very closely related. And it involves a little bit of a trick and some advanced calculus. And so if I define V to be gamma U, make sure I get this the right way around. Okay. Now, I just made it easier by making that gamma squared, so that I didn't have a square root there. That's just a little for the benefit of experience. Then you can do a calculation that you'll get del squared V, which of course you just have to do divergence, of grad gamma U, and then you have to use the product rule for that. So I won't do the whole thing. I'll leave it to. And then you have to do the product rule again. So I haven't written out the details, but after some more calculation in that vein, so it's probably more fun to actually do it yourself. So, so you work this out. Eventually you get, you then substitute in for this with the U's, and some things cancel out, and then you put back in the V's, and then you get this. So, put another way, where this is Q tilde. So in particular, for the EIT case, if I took Q equals 0 and gamma squared sigma, then U satisfying this equation is the same as V satisfying this equation. But the thing I'm missing out there is what happens to the boundary conditions, and it's easiest to do in terms of the Dirichlet to Neumann map rather than Neumann to Dirichlet map, and I think, well, again, this is something you just check with a little bit of calculus, that if you get the Dirichlet to Neumann map for one Q tilde, in other words, for this, the Dirichlet to Neumann map would be, I'll call it gamma squared Q, and that maps U restricted to the boundary to n dot gamma squared to U by dn at the boundary. Then this applied to some V restricted to the boundary is just gamma inverse. So I may make some small errors, but it's easy to check that. So the Dirichlet to Neumann map for V restricted to the boundary is you get your V, and if you do gamma inverse of it, and then you do the other Dirichlet to Neumann map, and then 1 over gamma, then it differs only by this term from the original Dirichlet to Neumann map. And especially if you take gamma to be, say, constant in the neighbourhood of the boundary, then this term disappears altogether. And in fact, if you take the constant to be 1, the two Dirichlet to Neumann maps are exactly the same. So you can see immediately that you couldn't possibly hope to find both gamma and Q from the Dirichlet to Neumann map, because at the very least you could trade off the gamma and the Q in this way. Okay, so that's kind of an aside. But it's worth you probably checking that you can do these calculations yourself, so that you can relate what we do for one inverse problem to another fairly easily. This change of coordinates, actually, to change a gamma into a Q, is sometimes called in literature the Bouville transformation. Although that's usually the transformation you apply to a second order ODE to put it in standard form. So it's that for PDE. Okay, so going back to what we did last week, we looked at the linearization of the forward problem for EIT, and the idea is that we end up with a system of equations to solve for a perturbation in the conductivity. So the idea was that we have conductivity change, sigma goes to sigma plus delta sigma, and then the boundary data U becomes U plus delta U, and then we measure either Dirichlet or the Neumann data that's the result of that change. And then, of course, what we actually have is we have some measurements of voltage or current at the boundary, and if we compare that with the voltages and currents we would have got for, say, some known case, say homogeneous, then we take the differences in the voltages and try and calculate a difference in conductivity. That's our delta sigma, and we add that to the one we assumed, right? So that's kind of linearized EIT problem, and in a discrete setting, we have a system of electrodes. So we actually have a vector of voltage measurements. Let me call that V vector. And these are the voltages for each current pattern. Voltage for each electrode for each current pattern. It would naturally form a kind of matrix, because each current pattern has all its voltages and then so on, but we just stack it into a vector. Okay? And we assume that delta sigma is a sum of SI times some basis functions, phi I going from 1 to m, say, and phi I of x, some basis functions. So the simplest case, you could take them to be constant on triangles or tetrahedra that divide up the domain into a triangulation. Or you could take wavelets or whatever nice basis functions you like. But in any case, the point is that these SI are then just coefficients to find, and we want and then the linearized forward problem is we've got some Jacobian matrix, which is the matrix of sensitivity coefficients, and the S is a vector of coefficients of the unknown connectivities, and delta V is the change in the voltages between the reference case of some assumed sigma and the ones you actually measure.